Let's talk about ultrasound. So ultrasound is actually the second medical imaging method that we talk about. Before I ask you to read the textbook, there are a few things I want to show you first. So first of all, let's take a look of our study guide first. And in the previous video, we talked about X-ray, and so X-ray were here. And then for ultrasound or ultrasonic, first of all, we have to talk about how they were generated in the medical context, and we will try to learn something called the acoustic impedance, the speed of ultrasound through the tissue and air, and something called the relative intensity level. There will be an equation useful here for calculating the impedance. Impedance is actually the letter Z, so here is the impedance. We'll talk about this equation later on. At the same time, we also have to explain the features of ultrasound technique, including the choice of frequency. There are something special. You cannot choose too high or too low, or in different situations you have to choose a higher one or a lower one. The reason why we have to use gel, in case you don't know, I'll show you a video later on what it means by using a gel. I'm pretty sure that you don't know, right, because you have never experienced that. Neither I, of course. And last thing is the difference between two ways of scanning it, which is A scan and B scan. Okay, so that's all you need to know for ultrasound. So first of all, again, before I ask you to read the textbook, I want you to take a look of this video, which is here, and I will put the link in the description. And this is a very good video showing you how the ultrasonic sensor or ultrasound can help us to detect the distance. And the basic idea is there is something called the piezoelectricity device inside, and which is here. I also want you to take a look of the Wikipedia as well. And well, first of all, let's take a look of this video first. So basically, you can read through, watch the video later on in the description by pausing the video. At the same time, I would like to tell you, so the basic idea is when you send a signal, it will go through quite few layers of organ. And after that, because wave is a wave, so it must have refraction and reflection. So by analyzing all those waveform, then we will be able to produce an image like how we could see right now. Okay, so I would strongly recommend you go to the link and try to watch this video. They got a very good explanation. So you may want to pause the video now. Okay, so for the Wikipedia, something I would like to share with you may not be very important for your IB exam, however, is that the discovery of piezoelectricity. So it was actually discovered and demonstrated more like successfully. You can see there's some other people try to work it out, but it was not very conclusive. So I think the first people or first person discovered the idea of piezoelectricity effect is the brothers Curie, and one of them, Pierre Curie, was actually someone that you probably know if you know about Marie Curie, which is his wife. They both, I think, is probably the only couple that has been awarded the Nobel Prize, right? Both of them. All right, I'm talking about both of them. And so not only one, but I think they earned like 3-4 times in their lifetime, which is very rare actually, like really super pure scientists. And then so basically these two brothers, they actually combine the knowledge of what has been done earlier, which is more about how temperature change will affect the electrical potential. But you know, for piezoelectricity, because just now when you finish watching the video, you know it's something to do with the mechanical pressure. So when you push the piezoelectricity like this one, when you push it, then you will generate a potential difference. At the same time, if you stretch it, then it would create an opposite potential difference. This is something very special. However, it's actually very small that people cannot observe easily. However, these two brothers managed to demonstrate it by using some natural crystal. The one that is the most famous is this one, okay, which is basically silicon oxygen. So it's something that we would still use it, of course, nowadays as a material for the ultrasonic sensor. Okay, so actually I find it's quite interesting. By that time, when they firstly discovered that they did not do the converse piezoelectric effect, that means if you again pay attention to the video just now, it actually told you that what happened at the beginning is when you push it, you can create a electrical potential, and in fact you can do it opposite. That means if you apply voltage to it, it will actually change the size of the material itself. Of course, it is not very noticeable, so that's why they didn't know until it was mathematically deduced by someone, right? Gabriel, this guy, mathematically using some other principles, and then they start to realize and do experiment to confirm the converse effect. That means doing the opposite, and they were successfully obtain the quantitative proof to show that actually it is reversible. So this is actually the most astonishing about piezo effect, because this is reversible. That's why what you can do is when you receive the signal back by the reflection, then you can change it back to electrical signal, and that's why we can use computer to analyze those signal form and create an image accordingly. Alright, so this is very amazing. The second video I want to show you is this one. In fact, you can actually go to some Shui-Po, OBGYN, to buy something like this plate. Alright, this is basically a piezoelectric generator. I think it just costs a few Hong Kong dollars if you go and buy it, and then you can buy on Amazon as well if you want. And this guy is demonstrating how you can use that to generate a voltage. So here it basically connected to the multimeter, and then you can see that when he press it, then it will change the voltage. Okay, and with some design with other component like capacitor, you will be able to build a very simple, should I say, torch, right? So basically you press it, and then you will be able to switch it on. Like now, okay? Like now, I think this is a switch or something, okay? So of course it's not going to be a very high voltage, so don't expect you can generate electricity for your whole home. You can't do that. You still have to rely on the main grid, but then this may help you to build some small devices. And the last video, I think, all right, and this, like, inside this video is here, which again I'll post a link in the description. And I'm just trying to show you the usual procedures for medical imaging using ultrasound, and I do think none of you has experienced being scanned, of course. All right, again, neither I never actually see it as well, but you can see this is something I want to show you. You can see this doctor, or I don't know how to call it, like technician, try to squeeze the gel onto her stomach here, and this is very important for medical imaging, for ultrasound, right? So without the gel, we cannot scan anything, and I will keep this as a question to you first, and we will explain later on. All right, we will get back to this. So you may want to think about, so how come we must need this gel? There must be a reason, right? No one want to actually get this gel on your body unless it is really necessary. Okay, so this is how doctor can scan the baby inside your body. Okay, so getting back to here, on quality, instead of your textbook, there is a really nice diagram where you can try to see, and here's the thing. So here's a probe, which means where it will send out and receive the ultrasonic signal. And inside your body, you may have a lot of different organs or your body parts, including your skin, the main body part, the stomach, and the bones as well. And imagine what you do is there is a wave sending out from here, and at this spot there will be some going backward already, while some will go forward, and this is called simply reflection, and then this is refraction, or you can also call it transmitted through it because it's 90 degrees. Also at this spot, at this boundary, again reflection and refraction will also happen. Same for this, same for this. Okay, and therefore you have a signal of this, you have a signal of this, and this at different time, because when the wave travel through it, that will take different time for it to bounce back to the probe. And depending on the density of the material, you may find there will be different amplitude, as you can see, which may show brighter or dimmer in the diagram. So this information can help us to determine the thickness of the organ. For example, your stomach along this line. Okay, and in fact this is actually called the A scan. For something connected with your prior knowledge, actually when we talk about reflection and refraction, actually that would coincide with what you learned in chapter 4. So imagine we talk about the free end and fixed end. That is what happens when you try to send a wave towards it, and it will actually reflect it backward. Same for when you have a rope that is thicker to a thin one, or thin one to a thick one. They will have different situation. Like one of them will have more reflection, one of them will have less reflection, and also phase change as well. So that will be related to what we will talk about later on. So right now, I think it's a good time for you to try reading the textbook on page 38 and 39. So pause the video now and we'll come back to this. Okay, so let me go through some key concepts that you should notice from the textbook. So first of all, you should know that the frequency of ultrasound in general should be higher than 20 kHz, and that's something to do with how much frequency you can hear, and that is referring to, if you want to, actually we have done that activity before, is that if you go to Google search tone generator, any one of them should do, and you can try to play some certain monotone. I'm not going to play here, but then you can try it, and then when you try to change it to maybe 20, then you will find out you cannot really hear, or you barely can hear it. While when you go to around 1000, not 1000, 18, oh, why is it like this? Never mind. When you try to change it to maybe around 20,000, or I think 18,000 already, you may not be able to notice and hear clearly anyway. So that is the audible range that you can hear. But then in fact, for the actual frequency that we will use for ultrasound, we will use around 1 to 10 megahertz. Actually depends, it's around this range. You don't have to memorize it, but I think some idea you have to understand. We would not use, since you know it's 20 hertz to 20 kHz, then you may ask, so why don't we use the lower frequency? That we'll explain later on why we don't use it. Okay, but we'll keep it later. First of all, if you try to compare ultrasound with X-ray, the brightest idea of ultrasound is it will not give any radiation dosage to the body. If you remember in the previous video, we talked about you cannot take X-ray too many times, or even CT scan. Like CT scan, you can't take really more than 5 times in a year. Okay, so ultrasound you can do whatever you like, no matter how many times you like, is fine too. And that is actually why it's very common that people would do it for scanning the baby, because who wants to scan their baby with X-ray when they are like simply growing? Radiation will be very influential and very damaging, especially for things that are growing. So that's why for kids, it's really not a good idea to expose them in radiation. While for adults, because they are kind of grown people, like you guys are kind of getting to adult as well, and your body is quite kind of mature, so it's quite stable already. While for the young kids, especially babies, you know the cell, if you study biology, you know something called mitosis or meiosis. They would start to have cell division, and by that time having radiation may help, not help, but may cause them to have mutation. So that's why it would not be a good idea. However, for the downside for ultrasound is that it would not be as detailed because of the resolution. I'm pretty sure if you simply just look at what we have here versus X-ray, those photos, I mean, you have seen in the previous video, or even you have taken one in your life, surely ultrasound is not very steady and the resolution is quite bad actually. Okay, so here in this paragraph, I'm not going to go through that with you, but the basic idea is to tell you how to choose the frequency. As we said, it's not easy to choose. It depends on the situation. So the constraint that you should think about in terms of the resolution is simply similar to for diffraction, right? When we talk about diffraction, where you can give the more obvious diffraction is when the size of the aperture is similar to the wavelength. So here we actually want the wavelength to be at most will be similar to D in that case. So right here, there is also another idea that you can try to approach to understand the best frequency is that for each frequency you may have different wavelength. So this is higher frequency, this is lower frequency. And imagine when you try to get back the signal, like how we mentioned, when it get back to you, obviously you want to have a full waveform. Imagine you only have like half of the waveform, then it will be very hard for you to produce the image because it's not even one wave. So that's why it said here that it has to be at least a few full wavelength, so then you can see what is that frequency at least, or identify that frequency. Otherwise it's hard to actually know what frequency it is. At the same time, you don't want much diffraction, because diffraction would get you to have noise basically. So like what we said earlier, this is diffraction. And imagine when you have your scanning, it would actually be the best if your wave, when it goes, it would be simply like no diffraction. So this is a case where there's no diffraction when you try to move like this. So going for a higher frequency actually would help to reduce the diffraction effect. And so this is one thing that is expected to know from the syllabus, but then when I try to look at quantity, and I find something more from other than from the textbook, which is here. Okay, let's take a look. So what it said is, for some reason, high frequency sound wave could be absorbed easily by the body tissue, and that's why it has a limited depth of penetration. And I think it's quite intuitive that for higher frequency, then it would easily be absorbed. And so in that case, for close, of course, I mean in general we like to have high frequency, but since it can only go through for a limited depth, then we can only use it for close surface. While for a deeper down in the body, if the high frequency cannot do it, then we could only rely on the lower frequency. Okay, so this is the idea of the choice of frequency. Back here in the textbook, there is a paragraph explaining how we can generate the ultrasound, and there are a few steps actually. The first of all, we have to rely on the piezoelectricity. So this is a word that you must know how to spell. Second thing is, as we talk about the piezoelectricity effect, is when you apply voltage. So this is the first step. What you have to say about is you apply the alternating voltage to it, and therefore it would vibrate in terms of that AC voltage. Right? If you have a higher frequency of voltage, then the vibration will be higher, and simply by that vibration, it would emit the ultrasound, because simply it's like your speaker. All right, there's a diaphragm, and then when it vibrates, and that would emit the sound. Okay, but then now it's simply the sound you want to emit very quickly, so you can use a piezoelectricity to help. And the best thing about that is, like we said, it can act as a receiver, because when ultrasound reflected back to the piezoelectricity, it will produce the AC voltage so that your computer can generate the image later on. Okay, so that is how it's been generated. And later on here, we would talk about the acoustic and impedance. And that's something to do with the degree of transmission. The way to calculate it is the impedance equal to the density, as you can see, density times the C, which is speed of sound in that particular medium. Okay, that medium only, not speed of light. And so for different medium, then they will have a different density and different speed of sound in that medium, and therefore different impedance. I will show you a table later on, but then there will be an example first. Okay, so I'll show you later on. But then here, the most important thing about finding out the impedance is we can use it and calculate the relative intensity level. So this is the relative intensity level for both reflected and transmitted. So you can see, if you try to look at the subscript here, R stands for reflected. You may want to write down in your Taskbook, and T stands for transmitted. Alright, and notice that this is not on your data booklet. Alright, let me show you. Okay, it's not on your data booklet. You cannot find it. Then will we get to use it a lot? Yes. Alright, I can guarantee to you. If that year they ask you about ultrasound, very likely you have to use this equation. Alright, then you may worry, hey, how can I calculate without having this formula in the data booklet? So I would say from what I observe in the past few years, they always give you these two equations, or one of the equations that you need. Okay, so in the question they will already tell you to use this equation or this equation. Alright, even though it's not written in the data booklet. So don't worry about that, and you don't have to memorize it. Alright, if you're really worried, then maybe just before an hour before the paper-free exam, take a look of this. You can maybe write this down on your personal data booklet first. Okay, and then maybe when you study for paper-free, then you can kind of short-term memory to memorize it first. Okay, but I do think they will provide it to you. Alright, as for the physics itself, I think it's actually quite interesting to see one connection mathematically between these two. Can you see that? Maybe you want to pause a video if you want to. Pause the video now if you want to. See what is the mathematical connection between them. Okay, so what's so special about them is if you try to add them up together, that means IT over I log, by the way, I log is the original, plus the IR over I log, what you find is actually you find it equals to 1. Alright, because physically you can already know that like what we do in laser is that when you send a laser to a surface, it will reflect, and will also refract. Alright, refract and reflect. Okay, and we talk about the intensity. It was 100, and maybe reflection is 6%. This is 94%, etc. This is simply conservation of energy. All right. So from the physics perspective, they should equal to 1. Okay. So let's just simply check whether it makes sense in terms of the mathematics itself. Right. We are not trying to say derive the equation, but we're trying to double check or to verify whether or not when they add up to, they will be equal to each other. So if you try to look at the fraction here on the top, you find 4, okay, maybe I'll write here, 4z1 c2 plus bracket z1 minus c2 bracket square. At the bottom, they are both z1 plus c2 bracket square. So that means as long as we can find out the top equal to the bottom, then the whole fraction equal to 1, right? And I think for some of you, you may be able to see it already, is that when you try to expand this thing, okay, just this, you will have z1 squared minus 2 z1 z2 plus z2 squared, right? And with this, then you would have 4z1 c2. And so if you try to look at this c1 times c2 and this one c1 times c2, the coefficient at the end, it would give you what? It will give you plus 2. And so once you get this, and I mean c1 square plus c plus 2 z1 times c2 plus c2 square, then that basically equal to this. All right, c1 plus c2 bracket square, and that is exactly 1. So quite beautiful, isn't it? And that also means if you somehow calculated one of them, let's say you find out this one equal to say 0.45, for example. All right, and that actually means for the reflected, in other words, you don't have to substitute anything inside. What you have to do is simply 1 minus 0.45, which is 0.55 in that case, because that's what you find out. Okay, so that is basically what you need to know for ultrasound so far. I will want you to do this example. So pause the video now and we'll check the answer. Okay, so this question is actually quite straightforward. What you have to use is the equation that we have, including impedance equals to density times C, and also that 2 equation probably. Okay, and so let's try to identify what is inside the question. So first of all, it tells you the density of air and the speed of sound, so which is C. So try to also have a habit of writing down the symbol next to it. The density of the soft tissue and the speed of sound in the soft tissue as well. So maybe you want to label them as air, soft tissue, S maybe, S for this. And then you just have to calculate impedance for each of them using this equation. For B, you have to calculate the fraction of intensity that would be transmitted. So using the first equation here, okay, the first equation here, and then just substitute the Z1 and C2 inside, and you should be able to find out the answer. And part C is to ask you a comment on the answer. Okay, so allow me to be lazy. I just simply use the answers from the Taskbook, and let's take a look. So first of all, you use this equation. You should find the answer for air is this one, for soft tissue is this one, and for transmitted fractions, that would be about 9 times 10 to the negative 4. That means if you simply have the ultrasound transmitted from air to the soft tissue, that means without anything, simply from air to soft tissue, then the transmitted fraction will be very low. The reason why it's very low is because most of them will be reflected because of simply the impedance between them. and therefore it is necessary to put this certain gel between the transducer, that means the probe or the ultrasound device, and the skin. Alright, so this is basically the reason why, back to that video, there is some sort of gel put inside. In fact, if you try to look into the equation, let me erase all this first. If you try to look at the equation of reflection and the transmitted intensity, you will find out one thing, especially for reflected, is that if you look at this number, it is Z1 minus Z2 squared. So that means if you want to have a lower reflection, so as little as possible, then what you would want to find is you want to get this to 0, no reflection, right? And ideally, what you can find is when Z1 equal to Z2, then apparently there's no reflection. And in fact, when you have Z1 equal to Z2, what does that mean? That means it's the same medium, isn't it? Right? So if you transmit it, if you're trying to send ultrasound to the same medium throughout, that means just like when we learn about optics, when you send a light through a medium, let's say this is glass, and if the next part is also the glass, exactly the same glass, and last layer is glass, then in fact nothing happened, right? There's no, you can apply Snell's law, but it is actually quite pointless. So same here is when you have the same medium, of course there's nothing changed, the wave will simply go straight. So of course there's no reflection. On the other extreme, that means if you have a really high reflection, right, as high as possible, then that means Z1 and Z2 will be so different. So either is one of them much greater than the other one, or Z1 greater than Z2, much greater than Z2. So if you try to look at just now, or the table from Cognity here, you see that for air, the impedance is very low, while for skin, it's very high. Alright, so you can see that's why this difference would make the ultrasonic wave to reflect mostly. And that is also why if you have to use a gel, then gel should have a similar impedance of this one. Okay, because one may argue, say, then what if we put the sensor very close to the skin, then maybe there's no air. Yes, technically you may say that, but then it's very hard, because when you have no air between the skin and the probe, then basically it's a vacuum, and I don't think anyone would want to have that. Alright, so we rather use the gel to fill up all the gap inside, and that gel has to be of a similar impedance to the skin. Okay, so that is the idea. One thing you may want to notice is for bone, then you can see, I mean, inside your body, like the diagram that we have here, alright, bone and the soft tissue, you can see that they are quite different in terms of impedance. So that's why for the bone, when you reach it, then pretty much most of them will be reflected. Okay, so that's why if you don't actually see much got almost, alright, after the bone. Alright, I think that is pretty much for this part.